My name is Erwin D'Souza. I'm a JIT compiler developer at IBM, and I'm also a committer at the OpenJ9 project. And I'm here to talk to you guys about an exciting project that we've been working on called JIT Compilation as a Service. But first, a slide to make the lawyers happy. So what is OpenJ9? You guys might have already heard about it before in the previous talks, but it is an independent implementation of a Java virtual machine, and you create a complete JDK by combining it with the class libraries from OpenJDK. And actually, it came from the IBM J9 VM, and in fact, the J9 VM right now, the IBM SDK actually currently uses and is built with OpenJ9. And so the project I'm going to talk to you about is actually prototyped using OpenJ9. So these are some of the things you might already know about a JIT, or just-in-time compiler. JIT compilation takes CPU time and memory from the application in order to compile and optimize code. And the idea is that if we run long enough, we usually break even. And while this has been true for big monolithic applications, it is less so for smaller distributed, shorter cloud-running applications. And the reason for that is because JVMs sometimes need to operate in small spaces. If you take a monolithic application that has been broken down into services, which is what you'd want to do if you want to run a cloud, each of these services might have their own JVMs, and in which case they might have their own JITs. And so there's a lot of duplicated work happening in these services. In addition, now that the services are smaller, you might decide, hey, we don't need that much space. Let's just take a machine, for example, in this case, 8 cores, 8 GB, and split it up into virtual machines. And in that case, you're now running a JVM in a constrained environment. So not only do you have duplicated work, where you're compiling the same methods over and over again, for example, methods in the string class or methods in hash map, but you're also limited by the amount of space you have in these machines. And so the question we asked was, what if we could JIT compile out of process, or on a different machine, or on a cluster of machines, and then maybe have the JIT have its own CPUs and memory resources, and serve multiple applications and share code between the different applications. And so the answer that we came up with was JIT as a service. The idea is to treat JIT compilation as any other cloud service. We ramp up and down resources based on load, and load here is compilation request. And by doing so, we can containerize it and manage it intelligently using Kubernetes or something. And we can share the results across the components and across applications. And what we're hoping for by doing this is we have better resource control for compilation and better scalability. Because the compilation or the JIT traditionally runs in process, it has to steal resources from the application. And it can only steal so many resources. If it took everything, then you wouldn't get any real work done. By moving it away from the JVM, we have the option of scaling it as much as we need to based on its requirements. We also get amortization of the cost of compilation because we can share the code across the different applications. It only has to be compiled once. We get improved reliability from the application because in the case where the compiler crashes, it doesn't bring down the entire application. It crashes somewhere else. And we can also now have better provisioning of resources for the application itself. The users don't have to worry about do they need to size their containers to take into account memory needed by the compiler or whatnot. Of course, there are concerns that we had as well. Network latency is a big one. Traditionally, compilation occurs at a time when the application is sensitive to ramp up. And by that I mean the time it takes to reach peak throughput. But now that we're moving it off process or on a different machine, we're at the mercy of the network. Security obviously is another big concern. We're now communicating on a channel that was previously completely internal to the JVM, but now we're speaking outside of it. There's also network reliability issues. What happens when you're in the middle of a compilation and the network breaks down? What is the fallback plan? And of course, the last one was, would all this work actually pay off? Would offloading it to a different machine work? And so where are we right now with the current prototype that we have? It's available on GitHub, and I put the 2 links up there for you guys. It is also there at the very end if you don't get a chance to take a picture now. It currently supports all the optimizations almost all the optimizations done by the OpenJ9 JIT. It communicates fully over the network by using raw sockets and protobufs, and currently it's a single server multi-client model, and it also supports OpenSSL. It can also run all the OpenJ9 test suites as well as many enterprise benchmarks. And so let's get a bit into this. At a very high level, it is a client-server model, as I mentioned before, with bidirectional communication. What happens is when the compilation begins when the compilation request is sent to the server, and it ends when the compilation server returns the compiled body back to the client. And during the compilation, the server can make an arbitrary number of queries to get information about the class info, profile info, hierarchy info. And the reason it needs to do this is because we've only moved the compiler off process. We haven't moved the entire JVM environment. And so the compiler has no notion about what is valid in this particular JVM's environment. And so in order to make optimization decisions, it needs to query the JVM, the client, about it. So let's get into it a bit deeper. There's 8 steps involved, and I'll go into each of these briefly. But I want you to notice that steps 1, 2, and 8 are essentially the same as what happens in an in-process JIT. We request a compilation, it gets processed, it gets compiled, and then we install it in the code cache. And so from the JVM's point of view, nothing has really changed. If the JVM doesn't need to know whether the JIT is in process or out of process. The separation happens at the JVM JIT interface. So in step 1, we generate a compilation request, which gets put in the compilation queue. Step 2, the request is processed by the compilation thread on the client. And the compilation thread here is a bit of a misnomer because it's not actually doing the compilation. It more facilitates the compilation. But anyway, once it processes the request, it sends the remote request to the server, where there is a socket listener thread that's listening for these requests. And when it receives such a request, it will place it on the compilation queue on the server side. And what it does here is not just place the request, but also the socket descriptor, so that when the compilation thread on the server needs to make queries against the client, it doesn't need to go through the listener thread. It can just directly communicate with the client. So in step 5, the compilation thread on the server will pick up the request and start compiling. And as I mentioned before, it will need to make runtime queries every so often. And then finally, when it's done compiling, it will return the compiled body back to the client, at which point we relocate, install it, and then the JVM now has a compiled body that it can run. And so that's the general process of how it all works. How does it perform? So I'm going to go through the 4 different areas of performance that we measured. Throughput, memory footprint, how does it perform in a constrained environment, and also how does it perform in the cloud, because after all, this is a service. So the setup we had was we ran it with 2 x86 Linux machines where we connected them with a direct Ethernet cable. On machine 1, we had the actual JIT server, MongoDB, and JMeter, each of them running in their own Docker instance containers. And then on machine 2, we had a Java EE Acmeer benchmark running on top of Liberty App Server. Acmeer is a benchmark that simulates a flight reservation system, and Liberty is a dynamic composable server application runtime environment. And so here's the graph we see for throughput. And by throughput, I mean throughput over time. The blue line is the baseline OpenJ9 with the in-process JIT, and the orange line is the OpenJ9 using JIT as a service. And as you can see, throughput is about the same. Ramp up is a little bit worse because of the network latency that occurs naturally when you're communicating over a network. And by ramp up here, I mean the time it takes to get from start to peak or steady state throughput. And so we don't have to sacrifice peak throughput, and the network latency is tolerable and can be mitigated for and optimized. Next, we look at memory consumption, memory footprint, and here specifically we measured resident set size. The blue line again is the baseline OpenJ9, where you see all the spikes that occur because of the compilation memory that needs to happen. Whereas the orange line is much more stable because we don't have the compilation overhead. All of the memory is dominated by the application and the heap. And so what we can take away from this is that the user doesn't need to worry about the JIT. They can just size their containers for their application and just move on. Next, we ran throughput in a constrained environment, and by this I mean we changed the Acmeer container to run it with only 64 megs of RAM and half a CPU. The green line here is the baseline OpenJ9, and the blue line is OpenJ9 with JIT as a service. And you can see that the JIT service run here performs much better. The reason the J9 run performs so badly is because it only has 64 megs of RAM, and so as the application's heap fills up, the compiler has less and less memory to work with, to the point where it can't compile anything and we're stuck interpreting. Whereas JIT as a service run doesn't have any of those problems because all of the compilation has been offloaded. It just gets the compiled body and can move on. We included a hotspot here because we wanted to verify to ourselves that OpenJ9 wasn't just performing badly. It basically just shows what a tough environment, a constrained environment like this is for a traditional JVM. If you're curious, the spikes are GC pauses. And then finally, we ran it JIT as a service for IBM Cloud Private, which I refer to as ICP. ICP is a platform for developing and managing on-prem containerized applications. And so we had 4 worker nodes here. One of them was OpenJ9 with the in-process JIT. Another one was running with the remote JIT server. We also had the actual JIT server, and then we had MongoDB. And so here is the performance we see for those that run. As you can, in the top left, we have throughput over time. And again, as you can see, throughput is a lot, is about the same here, but ramp up is much worse. And the reason for that is, unlike the other experiment, where the 2 machines were connected with a direct Ethernet link, which means that the ping time was about 0.2 milliseconds. Here, you're completely at the mercy of the network, and so the latency is much more obvious. In the bottom, you see the bottom left, you see the memory usage, and again, it looks about the same as the previous slide, where the JIT as a service line is much smoother and represents really the heap, or whatever is in the resident set size of the heap. On the top left, you see the CPU usage of both the in-process JIT and the JIT as a service client. There's a big spike in the beginning on the baseline because you have all the compilation occurring, but you don't have that big spike with the JIT as a service client. You do, however, have more memory use, more CPU usage than one would expect. And the reason for that was because of all the network communication. It was kind of a shock to us that network communication took up that much CPU, but it's something that we're now looking into mitigating. And at the bottom right, you see the CPU usage of the server, which you can see is more spread out because one of the network latency aspect. And it's also more than it should be because along with the compilation, it's also suffering from the network CPU usage problem. So that's where we are with the JIT as a service model right now. Where are we going with this? Well, first, we want to now work on sharing compilations between clients. The prototype as it stands right now is a one-to-one model where if you have 2 applications and you connect to the server, it will compile the same method twice. But that's not something that needs to be done, and really, it may help in a constrained environment, but you don't get the cost of the amortization benefits of doing so. We want to finish implementing the remaining optimizations so that the JIT as a service run performs equivalent to the baseline run. We want to experiment with mixing local or remote compilations so that as a mitigation factor for what happens if the network goes down. I mean, maybe it takes so long, or maybe the server is so bogged down with requests, you don't want to wait too long to get your compiled body. Maybe it's better to just compile it locally. We want to improve latency, of course, for the CPU, partly to improve ramp up, partly to deal with the CPU resources, but also the experiments that we did before, we ran without encryption. The moment you enable encryption, as the prototype stands right now, every single compilation request will do the handshake, which means that we reduce ramp up even more. And so that's another thing that we want to look into, where we can try and maybe cache the handshake once it's done so that we don't have to keep doing it over and over again once we've established a connection that we trust. And finally, we want to merge this back into the OpenJ9 master. Currently, it sits in Eclipse OpenJ9, but in its own branch. And a lot of work has been done to sort of separate it and have it run independently, but eventually we do want to move it back so that it's one big happy project. Here are some links, as promised. The top 2 links are the source code you can get and take a look at. It is very much active development and an area where we're more than happy to get contributions and suggestions or whatever ideas you might have. Feel free to message us on the OpenJ9 Slack channel. I included the OpenJ9 website so you can get instructions on how to join the Slack channel. The link is way too big to put here. And finally, if you're interested in a demo, which I was not brave enough to do, one of my coworkers did a demo at Code One, and so you can follow the YouTube link and take a look at how all of this works. And if you have any other questions, feel free to ping me or the OpenJ9 Slack channel because people are actively listening. That's it. Thank you for your time, and I'll take any questions if you have any.
So thanks, those are interesting. So how many requests do you, back calls do you do usually for a compilation?
So because I don't directly work on this, I don't know the exact numbers. I do know it's a lot, and they have been working on reducing it quite a bit, because in the beginning it was just ridiculous. I don't have exact numbers though, but if you either email me or you message on the Slack channel, the people who are working will either email me and I'll forward the request, or message on OpenJ9 Slack and they'll have answers for you. I don't have it offhand.
Could you give some indication of what data you're passing in the initial request and what type of data you have in the back request?
So I'm not sure of obviously all the details, but we do pass the bytecodes obviously, as well as some other, I'm not sure in the beginning what metadata is sent. For sure the bytecodes, and I think the bytecodes of the entire class of the method, just in case it needs to inline other things. When we send it back, we send metadata about how to relocate it in the new space, as well as stack maps, inline table, GC maps, all of that information that it needs so that it can install it properly and do all the right, when a GC occurs, it knows what's going on and whatnot. So that's the information we have to send back to the client.
What about profile data?
So profiling data we request, I believe, in between. So the profiling happens in the client, and if we need profiling data, we just sort of, normally we have an iProfiler, we'll just say, iProfiler, give me a request. But now that's been separated over an API. So we'll just say, give me iProfiler data on the client, because the compiler doesn't really know. It just says iProfiler data, goes over the network, client gives it back. And it does so with protobuf so that it can maintain the structures and whatnot.
Did you look at security issues for the compiler itself? Because now the code can trigger, for instance, buffer overflows in the compiler.
Yeah, so I mean, security is something that is obviously going to be a concern. Right now, it's still very much in the prototyping stage. We've sort of looked into for the security of just the communication, so you don't have any problems there. But in terms of the server, the compiler, you're right. There's going to have to be eventually, more time spent into making sure that we are mitigating every single possible, because we don't want to send obviously code that can now disrupt the server. I mean, or bytecodes or whatever. You have to have some notion of this. The client is a trusted client, but obviously it's still prototyping, so we haven't got that far into the specifics. But you're right, security is still very much a concern that's not going to go anywhere, especially when you go distributed.
I have two quick questions here. One is, have you considered the use case of using it locally? Because it seems like you're very much focusing on over the network, but it seems to me that with the current way of having containers, if you have like one container, which is the compiler, and then many containers with the VMs, you could share them.
You definitely could. It's talking over the network, but if you define the whole idea was remove it out of process. So that way, you're right, you could just have, if you change the communication protocol, you could easily have it so that, you have one container and then talk to the other ones. I guess this is a more general problem of like if your containers are running on one provisioned set of resources, then maybe it's better to move it somewhere else. But you definitely could do it that way too. Yes.
And my second question is, now that you have the compiler completely separate from the VM, have you considered playing with like changing the compiler a lot, or plugging in other compilers now that it's quite separate?
So, because this is done in OpenJ9 and the compiler JVM interface is quite tight, you would need to re-implement all the. You could do, as long as you implement the JVM JIT interface levels. I suppose theoretically you could try and plug in a different compiler if you had it. It's just you would need to talk to the OpenJ9 VM in the same way, and know how to interpret the data in the same way. But again, theoretically, yes, you're right, it could be done.
Have you looked at checkrack core, and are you signing the codes that you are sending over the network?
Right now, I don't know. If I'm actually not sure about the answer for that, because it's still very much in the prototype phase. We just sort of have a network call, and I guess the network call could be augmented to do what you're saying. But at the moment, we're still trying to get it, going to a better standard than it is right now. We're still improving it. So, but if you want a proper answer, yeah, just email me or ask the Slack channel, and the people who know more about it will be able to answer you for sure. Yeah.
Wait. We're streaming this.
Would it make any sense to actually kind of replace the on-demand compilation with kind of ahead of time compilation? Because at the end, when you start the app, you technically can send like the whole application to the cloud, JIT compile, and
yeah. So I mean, OpenJIT does have AOT after all. But one of the big problems with AOT is if you specialize too much, you lose the ability to share. Meaning that it's very like all you need is one. Let's just say you got profiling information in one run and that happened to work. It may not work in the second run, in which case you can't share that code anymore. And so with this one, you get a one-to-one mapping for each one. Now, of course, when it comes time to share code, you're gonna have to deal with the same problem where you need to find what is the best answer. But that's that is the other area of what you can do in this case. This is again a general problem for when you have constrained environments, for example, where you want to have all your services. You can't afford to sort of pre-populate your cache on the machines that are running the service. So maybe it makes more sense or you're running in a cloud environment where you don't know where these things are and where the cache is going to sit. You just have machines generated for you, just like they just popped up. So in that case, it's harder for you to say, I'm going to put the cache over here. It becomes a problem almost what's all over here, where it's have a thing that'll do it for you. And at the end of the day, with the sharing, there's you can share on the client side, you can share on the server side. It's what we're going to do is still an open question, and I mean suggestions you have are more than welcome, including if you want to if you have any ideas or whatever, we're more than happy to listen to you guys and take into what you have to say.
Thank you.
No problem.
Right. Thank you very much.
No problem.